Hello everyone, my name is Archiki and today I'll be presenting our EMNLP paper, ReCEval, Evaluating Reasoning Chains via Correctness and Informativeness. This work was done at UNC Chapel Hill in collaboration with Swarnadeep Shang and Mohit Bansal. Most prior works rely on the final answer to evaluate reasoning chains. However, this may confound reasoning abilities of language models with unfaithful or spurious shortcuts. As shown in this example, the language model can achieve the right answer despite the highlighted errors in the reasoning chains. Other works suggest reference-based evaluation on goal reasoning chains. However, getting these annotations can be expensive and time-consuming. In some instances, a problem can have multiple correct goal chains which can negatively impact performance. Before moving ahead, we ask what level of granularity should we use when examining reasoning chains. One natural choice could be steps, however, step boundaries are determined by the language model. To allow for more fine-grained evaluation, we introduce the idea of reasoning content units or RCUs. We consider each step to comprise of one or more claims represented by an RCU in blue brackets in this figure. We assume that each step will always contain one conclusion RCUs and the other units will be premise RCUs. We argue there are two desired properties of good reasoning chains. First, every step in the reasoning chain must be correct. Specifically, we are concerned with intra-step correctness that ensures consistency of claims or RCUs within each reasoning step, as well as inter-step correctness that evaluates global consistency considering input and preceding steps. Next is a property of informativeness that assesses the importance of each step in advancing towards the model's final answer. Lack of informativeness manifests as repetition or redundancy in the reasoning chain, even though it may not impact correctness. Using this example, we show how to compute intra-step correctness using the premise RCU and the conclusion RCU within the same step. The evaluation can be done using the entailment probability of the two units or using a fine-tuned T5 large model to compute point-wise V information. For more details, check out the paper. Next, to evaluate inter-step correctness of a step, we measure the lack of contradiction between the conclusion RCU of the step with respect to the input context and conclusion RCUs from the previous steps. To measure informativeness, we compute the amount of information contributed by a step to predict the model's answer conditioned on the preceding steps. The overall algorithm begins with identifying RCUs and classifying them as premise or conclusion. Then we use the RCU information to compute step-level scores for each metric. Finally, we aggregate these scores across steps using the minimum operation for each metric. This means that we measure the least correct or least informative step in the reasoning chain. Here is an overview of our experimental setup. We work with three reasoning datasets: entailment bank, GSM8K, and drop. For baselines, we use text generation metrics as well as ROSCO, a recently proposed reference-free reasoning evaluation metric. Finally, to compare performance of baselines, we compute Somers-Lee correlation between a metric score and a binary variable indicating absence of errors. For each dataset, we present Somers-Lee correlation for specific error types represented by the columns. Next, on the same dataset, ReCEval outperforms ROSCO on identifying 5 out of 6 error types. Consistently, on GSM8K, we find that ReCEval beats all text generation baselines. Also, ReCEval outperforms ROSCO on the overall quality and coherence measures in the first two columns, as well as at identifying 5 out of the 7 error types. Once again, on the drop dataset, ReCEval outperforms ROSCO on the overall quality measure and at identifying 5 out of the 6 error types. Next, we show that prompted large language models can be incorporated within ReCEval by prompting the LLMs to generate real-valued scores for correctness and informativeness as shown in this table. This shows the flexibility of ReCEval to be used with diverse language models. Finally, we study whether scores from ReCEval can yield downstream improvements in task performance on the GSM-8K dataset. As this table shows, selection and ranking based on ReCEval scores yields the maximum downstream task improvement. In summary, we present ReCEval, a reference-free evaluation framework for reasoning chains. ReCEval evaluates reasoning chains based on correctness and informativeness to better identify possible errors. Finally, we show that it can be used with diverse language models and improve downstream task performance. Thanks for listening. You can refer to our paper or code for details.